So, have you ever seen this happen? You watch an AI agent, it starts a task brilliantly, and then it just spirals completely out of control. It's super common and honestly pretty frustrating. Well, today we're going to unpack exactly why that happens. And the solution, you'll see, comes from a surprisingly old-school place. Let's dive.
Right? We've all been there. You give an agent a pretty complex task. The first couple steps, flawless. And then, all of a sudden, it starts repeating itself over and over, or it just hallucinates some totally bizarre, out-of-left-field details. It completely loses the plot. It feels like the agent just, well, it breaks.
And our first instinct is to blame this on the AI's intelligence, right? Or maybe its lack of intelligence. But what if we're looking at this from the wrong angle entirely? What if this isn't a problem of intelligence at all, but a problem of stability?
And this is where things get really interesting. The key to fixing our super futuristic AI agents might not be about cramming in more training data or building even bigger models. The answer might actually be hiding in the principles of control theory, an engineering discipline that's been stabilizing systems since, like, the 1950s.
Okay, so first things first. Let's get a really clear picture of what we actually mean when we say an unstable system, and why that's a much better way to think about these AI failures.
Let's just put the main idea right out there. This is the core thesis. When your AI agent fails, it is not having a failure of intelligence. It is experiencing a failure of control. It's an unstable system that is spiraling into chaos.
To really get this, think about a racing drone, an FPV drone. When it's not tuned right, a pilot tells it to do a simple flip, and it just overshoots, wobbling and oscillating like crazy. That is exactly what an AI agent is doing when it gets stuck in a repetitive loop. Or when that drone starts drifting in the wind, the pilot has to constantly nudge it back on course. Sound familiar? That's you, constantly reprompting a drifting AI to get it back on track. The underlying physics of instability are pretty much the same.
So, how do engineers actually solve this kind of instability? Well, it all boils down to two very different, fundamental ways to think about control. So on one side, you've got open-loop control. I like to call this the run-and-pray method. You just give it an instruction, cross your fingers, and hope for the best. The output has absolutely zero effect on what the controller does next. Think of a cheap toaster. You push the lever, set the timer, and it just runs. It doesn't care if your bread is perfectly golden or if it's become a charcoal briquette. Then you have closed-loop control. The motto here is run, measure, adjust. The output is constantly measured, and then, this is key, it's fed back to the controller, which then adjusts its actions. This is your home thermostat. It's always checking the room's temperature and turning the heat on or off to stay right on target.
And the secret sauce that makes all of that possible is the feedback loop. This is probably the most crucial concept to get. It's a self-correcting cycle where the system is always watching what it's doing, comparing that to the goal, and then making tiny adjustments. You have to remember, without feedback, there is no stability. It's just not possible. Now, let's get into the weeds a little bit and look at the most common tool engineers use to create these super stable closed-loop systems. It's called the PID controller.
So PID stands for proportional, integral, and derivative. Each part has a really specific job. The P, proportional, reacts to the error happening right now, in the present. In our drone analogy, this is its responsiveness, how snappy it feels. The I, integral, corrects for errors that have built up in the past. This gives the drone its stiffness and stops it from drifting. And finally, D, derivative, tries to predict future error. It acts like a dampener to stop the drone from overshooting its target.
But here's the catch. You can't just crank all these settings to the max. The real key here is balance. Tuning a PID controller is a genuine art form. If you have too much of any one of those components, the whole thing just goes haywire and becomes unstable all over again.
And hey, don't just take my word for it. Listen to this quote from drone expert Oscar Lang. He says that if the P gain, that's our responsiveness factor, is too high, the drone overcorrects, and you get sharp bounce backs and oscillations. Remember that word, oscillations. It's going to be important in a minute.
Okay, drone racing is cool, but let's connect all this back to our AI agents. One of the most powerful techniques that we use today is something called chain of thought prompting. And as we're about to see, it is a fundamentally open loop and therefore unstable system.
So what exactly is chain of thought? Well, the idea is actually super simple, but really powerful. You just ask the model to think step by step, to generate all of its reasoning before it gives you the final answer. And honestly, it's dramatically improved how well AIs can reason through problems.
But here's the massive catch. Standard chain of thought
is just like trying to solve this maze by drawing out the entire path before you even take your first step. If you make a wrong turn, way back at the beginning, there's absolutely no feedback mechanism to tell you that you've hit a dead end. The agent just keeps going, following that wrong path, digging itself deeper and deeper into a hole. It is a run-and-pray system, plain and simple.
So, if chain of thought is an open loop, the solution is, well, it's pretty straightforward, right? We need to close the loop. We need to build a self-correcting agent.
And here is what that actually looks like. It's that beautiful run, measure, adjust cycle we talked about, but applied to an AI. First, the agent generates a thought. Then a second process, a critic, measures the error in that thought. That error measurement gets sent back as a feedback signal. And finally, the agent uses that feedback to adjust its next thought. It's a constant, beautiful cycle of self-correction.
And this is the real payoff. This is the big aha moment where it all clicks together. We can literally map AI settings directly to control theory. Think about the temperature setting in a large language model, the one that controls how creative or random it gets. Setting that temperature too high is exactly like cranking up the P gain on our drone. Sure, it makes the agent's responses more snappy and creative, but it also makes it wildly unstable. It overcorrects. And those sharp oscillations we saw with the drone, in an AI, that's what we call hallucinations.
So let's bring this all home and ask that central question one more time.
The next time your AI agent goes completely off the rails, try not to think of it as being dumb. Think of it as being untuned. The massive power for reasoning is all there, but it's being applied in an open loop. The problem isn't a lack of intelligence, it's the total absence of a feedback loop to provide stable control.
And that's really the thought I want to leave you with. We are so focused all the time on the absolute cutting edge that sometimes we forget these foundational principles of engineering. And it makes you wonder, if a theory from the age of vacuum tubes can solve a core problem in our most advanced artificial intelligence, what other powerful, timeless ideas have we overlooked in our rush for the new?